Hello, today I want to talk to you about the Diels-Alder drawing tool. We talked previously about using rules for stereochemistry to determine the stereochemical outcome of the reaction. And I want to work through how to use the drawing tool. I know we talked about this in class, but I want to work through it here so you can think about it a little bit more on your own watching the video. So what I want to do is work with these two problems. These are problems that we worked on in class previously, but let's work through them using the drawing tool. Right? So we have one example of an intermolecular Diels-Alder, one of an intramolecular Diels-Alder. And I think if we work through both of these, we'll see how we can apply these to the problems that we're working on. So let's look at this one. And one thing that's really important to recognize when you're using the drawing tool is you always, whether you use the drawing tool or just following the rules, you always have to figure out the regiochemistry of the intermolecular reaction. All right, so first step is to determine the correct regiochemistry. All right, and as always, we're going to find the most electron-rich atom of the diene and make sure that reacts with the most electron-poor atom of the dienophile. Right? So again, electron-rich from the diene plus electron-poor from the dienophile. Right, and we've done this sort of thing before where, we say, all right, methoxy is our electron donating group. It's going to donate in, and it's going to make that atom electron rich. Right, nitro is the electron withdrawing group. If we drew out what nitro would look like, we would pull electrons toward the nitro group, making this atom electron poor. All right, and so that's the strategy that we're going to use. Again, when you look at the product, you can use what we've called the ortho-para rule, but I think this is a better strategy for us to use. Right? So we can see that for these two things to react, we're going to have to flip over the dienophile so we get the correct regiochemistry for the reaction. So let's redraw what that would look like. And again, D here, as we've seen before, is just deuterium. So we've just flipped over the dienophile, so we have the electron-rich atom reacting with the electron-poor atom, and that's going to give us the correct regiochemistry. All right. So now when we think about what's going to happen in this reaction, and again, this is just our standard thermal Diels-Alder reaction, we have to think about how are these two things going to interact, and the drawing tool enables us to show how that happens. Right. So for our drawing tool, so we determine the correct regiochemistry. So now we're going to draw the diene above the dienophile, right, with the W group underneath the diene. All right, and the W group underneath the diene is so that we are using a model to approximate what happens with the secondary orbital interaction, where the pi bond of the dienophile interacts with the internal p orbitals of the diene, right? So what is that going to look like? So we're going to draw our diene. And then we want to draw the dienophile underneath it, and with the W group underneath the diene, all right? So for us, when we draw it in this orientation, so the diene open to the right, W group underneath the diene, so it's going to be pointing to the left, all right, underneath the diene. All right, so let's draw what that would look like. So essentially we take this dienophile and we flip it over, right, so that we have the dienophile underneath the diene, W group pointing to the left. And again, what would happen in the actual reaction is that the pi bonds in the nitro group or the carbonyl or whatever the withdrawing group is would interact with the p orbital here. That's the so-called secondary orbital interaction, right? And so the ethyl is on the same side as the nitro, so that ends up over on this side, and the methyl is pointing the other direction, so that ends up over here. So we'll just put a CH3 there so it's clear, all right? And so what the drawing tool enables us to see is that which atoms are going to end up on the same face in the product, right? And so what we do now is we say that there are two regions that are going to have substituents cis. So what you want to do is just extend the diene. So just draw out to extend where the diene is. So essentially I'm just extending that diene bond so that we have two regions that we're going to look at, right? We have one region here that we're going to call inside, and then we have another region that we're going to call outside. And again, that's completely defined by looking at extending the diene and saying, in that opening, there's stuff inside the opening and there's stuff outside, right? And the neat thing about it is that this tells you what's going to happen. It tells you that the deuterium in this methyl group will end up cis to each other in the product. It tells you that the ethyl, the nitro, and the methoxy will end up cis to each other in the product, right? And then whatever is outside is going to be trans to whatever is inside, okay? And so what does that look like when we draw the product? So if we say that, and another way to think about it is these two things are on top of each other, and then we're going to uncurl them. And if we uncurl them, these things will end up pointing out at us, all right? So the deuterium is going to be on the dienophile, or sorry, on the diene carbon, so that's going to be here. So the deuterium will be pointing out at us. The methyl is on the dienophile carbon, which is that one. That's going to be pointing out at us. And then the other groups, the ethyl, nitro, and methoxy, will all be going back. So the ethyl's going back. The nitro is going back. And the methoxy is going back. All right, so using this drawing tool enables us to get to this product, you know, and again, as we said before, it's this plus the enantiomer, all right? But again, you can use the rules or you can use this strategy to figure out what the correct product looks like for the Diels-Alder reaction, all right? So when we did this one, first we did the regiochemistry, then we started doing the drawing where we drew the diene, W group underneath the diene, W group on the dienophile underneath the diene, stuff in this area inside, cis, stuff in the area outside, cis, trans to each other. If we do this for the intramolecular reaction, it looks very similar. We just don't worry about the regiochemistry, because in intramolecular reactions, especially when it's a reasonable size molecule, you don't have to worry about regiochemistry. There's no way you can flip the dienophile and get a reasonable type ring. So for something like this, let's just redraw it so it actually looks like a Diels-Alder can happen, right? So if we rotate this bond, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, we have 11, so that's 1, 2, 3, 4, 5, 6, 8, 9. So 6, 7, 8. 8's got a carbonyl on it, and then we have our double bond, and it's trans, so it's going to look something like, it's going to look something like that. Okay. So that's 8, 9, 10, and 11. All right, and that's really the only way we can orient this compound so that it'll do the Diels-Alder, right? It's going to react like that. All right, and usually what I'll do is just draw out what the skeleton looks like and then do the drawing tool to figure out the stereochemistry, right? So if we draw out what this is going to look like, we get our 6-membered ring, methyl group. We're going to get a 1, 2, 3, 4, 5-membered ring here, right? So that'll be a 5-membered ring coming off in that position, methyl, ketone, right? And again, you can number that to make sure we got it right. Okay, and so now we want to figure out what the stereochemistry looks like for this, right? If we use the drawing tool, do the exact same thing we just did, draw the diene, open, pointing to the right, and those are the substituents coming off of the diene. Now draw the dienophile W group underneath. And then we can just connect them, right? So again, 1, 2, 3, 4, 5, 6. This is 8. So carbon 7 is there. 7, 8, 9, 10, and 11. Right? And the key here, again, is that we have the W group underneath the diene. So it's demonstrating what this is going to look like in the reactive conformation. Right? Do the exact same thing we did before, where you extend out the diene. Right? And what does that show us? It shows us that on the inside, all we have is the methyl at 11. So if we redraw to figure out the stereochem, so the methyl at 11 will be coming out at us. And then if we look at what's outside, it's everything else. So carbon 1, carbon 8, carbon 6 are all going to be cis to each other, and we'll say that they're back. So we get that as our product. And again, it's this plus the enantiomer. Okay? So again, hopefully this is useful. And I know some of you prefer not to use the drawing tool. That's perfectly acceptable. It's just another way, if you don't want to memorize what the rules say, you can just use this drawing tool, draw what the reactive conformation looks like, always remembering that the W group goes underneath the diene, and then sort out what it's going to look like.